Hello, today we are going to derive the expression for electronic heat capacity. That is the electronic contribution of heat capacity of a metal. So let us consider the metal is heated from 0 to T Kelvin. Okay, so the increase in energy, internal energy, or the total energy of the sample, total increase in energy of the sample is equal to the final energy minus initial energy. Okay, this is the change in energy. What is energy at T? This is equal to integral 0 to infinity E energy of a particular level into density of state of that level into the probability of finding electron in that level. So that is the Fermi-Dirac function into dE. So this is the energy. Now we are integrating from 0 to infinity. So we have many energy levels, okay, like that. So E is some energy and the density of state is like this thing. So f of E is the Fermi-Dirac function corresponding to that particular energy level. Now the total energy is obtained by the energy into the number of particles. The number of particles in that level is equal to d of E into f of E. So now we are integrating E into n of E dE. Okay, so this is nothing but n of E is equal to d of E into f of E. So this is u of t minus u of 0 is at 0 Kelvin all the electrons are below the Fermi energy. Okay, so if this is Fermi energy, if all the electrons will be occupied within this. Okay, so this is equal to 0 to integral 0 to EF E into d of E. F of E will be at t equal to 0, f of E is equal to 1 into dE. Okay, so this is equal to integral 0 to infinity E d of E f of E dE minus integral 0 to EF into d of E d. So this is the total energy change if we are heating from 0 to T Kelvin. Now the total number of electrons or particles is equal to free electrons is equal to n is equal to n is given by 0 integral 0 to infinity d of E f of E dE. So this is the total number of electrons in a metal. Okay, free electron in a metal. This is also given by this is also equal to if at t equal to 0 all the electrons will be occupied within the Fermi energy. So that is explained by this equation integral 0 to EF d of E. What's f of E? If at t equal to 0 f of E is equal to 1. The probability of finding an electron in an energy level with less below EF is equal to 1. So that will be equal to 1 into dE. Okay, so this is at t equal to 0 Kelvin. So this is at a general value of, if we substitute t equal to 0 Kelvin, this value will become f of E is equal to 1 and this integral becomes 0 to EF. Okay, so that's it. Now we multiply by EF, we will get n into EF, that is integral 0 to infinity EF d of E f of E dE is equal to integral 0 to EF EF T of E D. So we have multiplied this n by EF. Now this integral can be split into 0 to EF EF T of E F of E dE plus integral EF to infinity EF D of E F of E dE is equal to integral 0 to F, right hand side, EF T of E dE. So the same integral we have split into 0 to EF and from EF to infinity. So that will be 0 to infinity. Now use this expression in the expression of delta U. So delta U also we can split this integral 0 to infinity by 0 to EF, and from EF to infinity we can split this integral also. Okay. Therefore, let me write delta U once again here. Delta, this is equal to 0 to first EF E D of E F of E dE plus integral EF to infinity E D of E F of E dE minus, so this is U of t minus U of 0 is integral 0 to EF E D of E into F of E is 1. Okay, so this is delta U. So we can use this identity, this equation number 2. So this equation we can use in this expression. So I will subtract these two terms from this, and then I have to add this thing. Okay, so I can add this thing also. So these are the equation 2, the right hand side and the left hand side are equal, isn't it? So I'll subtract this left hand side and then add this right hand side from this delta U. So it will not change the value. So this is equal to integral 0 to EF. So integral 0 to EF is here, integral 0 to EF is there, E d of E F of E d. This is EF d of E F of E d. So this will be E minus this thing. So E minus EF, integral E minus EF d of E F of E dE. Then this minus this thing. This is also integral. This integral is from EF to infinity. This also from EF to infinity. So I can combine these two. So I have to subtract this from, sorry, this from this thing. Plus integral from EF to infinity E minus EF d of E F of E d minus integral from 0 to EF. Now this is the term. So I have subtracted this thing. Now I have to add this thing. So minus, so I'll write this thing as plus EF minus E d of E d. So this is the value. So the value of delta U didn't change because I have subtracted and added. This is equal to, so I can combine this thing. So there is 0 to EF is there here. This also from 0 to EF. So I can write integral from 0 to EF E E minus EF D of E F of E D. This is EF minus E. So this can be written as EF minus E, EF minus E, D of E is there, D of E. This is common to this and this, but this will be E minus EF. So I can write this is 1, okay, 1 minus F of E D. So from integral is this integral is from 0 to EF. I have combined this and this, so you can write like this, plus from EF to infinity E minus EF T of E F of E. Okay, so this is delta U. We have two integrals here. One integral is this from 0 to EF and the other one integral is EF to infinity. So we can write, so we are taking this metal from 0 Kelvin to T Kelvin. Okay, so T Kelvin we are rising. So that means this is EF. Initially all states are occupied by electron within the Fermi energy level. Now when it is raised to the temperature, some of these electrons will go to higher energy levels, okay, beyond this EF. So that means what? We have to take all these electrons to EF first. For example, if this electron is raised to some higher energy, so first we will take these electrons into EF, then from EF to energy, some energy E. Okay, so if one electron is raised from this to this, that means first to EF, then EF to that particular energy. Similarly, other electrons also. So the first integral, this is the energy required to raise the electrons from level below the EF to EF, and from EF to another energy level E above the EF is the second contribution. So from EF to now the heat capacity. This heat capacity is because of the electronic contribution. So that is why C electronic is equal to du by dt. We have to differentiate this thing with respect to temperature. So here EF is not temperature dependent, energy is also not temperature dependent, density of state doesn't have any temperature dependence. So here only dependent quantity is F of E. F of E, we know what is F of E. F of E is equal to 1 divided by E raised to E minus mu divided by KT plus 1. Therefore, if we differentiate this equation, we will get 0 to EF, EF minus E into D of E into minus, that is, this minus is there, minus df divided by dt, df of E divided by dt dE, plus from 0 to, no, from EF to infinity E minus EF D of E df divided by dt, because only F is temperature dependent, okay, into dE. Okay, so this is minus of EF minus E. This also will become E minus EF. So the same integral. So we can combine this two integral into integral 0 to infinity E minus EF D of E df divided by dt. So this is the uh, electronic contribution of the heat capacity. Now we have to find out, we have to evaluate this integral. Okay. So here, one more thing is to be noted, that this integral can be written once more like this. This can be d of e minus ef df divided by dt into dE. This e minus ef df by dt we have plotted a graph before. When t equal to 0, this is ef. When t equal to 0, this is the graph, and when t increases, the graph become like this. Again, further increase will change the graph like this. So what happens near ef, e equal to ef, the df by dt is what? This is f, this is energy for a given energy. Let me take this thing. At this e, this is f value, this is f value for the temperature, which is less than this temperature. So here T1, T2, this is T1, T2, T3. T1 is equal to 0 anyway. So when temperature changes, the value of F also changes. This dF by dt into E minus EF will have a peak. That means E minus EF dF by dt will have a positive peak near E equal to EF. At this value, near this value, E minus EF dF by dt, this quantity will have high positive peak. Okay. So we can write d of E. So then we can write d of E can be written as E of EF, because E is near EF. So d of E will be equal to d of EF. Therefore, C electronic contribution is equal to integral 0 to infinity d of EF E minus EF dF by dt into dE. Okay. Therefore, we can write this thing as this is d of E. What is d of EF? D is density of states is equal to 3n divided by 2E. So d of EF is equal to 3n by 2EF. Okay. So that is anyway is a constant. EF is a constant. Number of free electrons is constant. Therefore, d of EF integral from 0 to infinity E minus EF dF by dt into dt. Okay. Now first we want to find out dF by dt. Differentiation of the Fermi-Dirac function with respect to temperature. So this will be equal to 1 divided by e raised to e minus EF divided by kt plus 1 square. Okay, minus of this thing. So this what is dx by dt? If we differentiate this thing, this is equal to e raised to e minus EF divided by kt into, now we have to differentiate this thing, minus EF divided by kt square it will be. So we have to differentiate minus 1 by t square. E minus EF by k is a constant. So the differential of 1 by t is minus 1 by t square. Okay. Therefore, the heat capacity per unit volume, the electronic contribution is equal to dE I can make into d of E minus EF, isn't it? Because EF is a constant, therefore I can write this thing as, you can write this equation as, now let us put E minus EF by KT as x. Therefore, when E equal to 0, x become equal to 0, then x equal to minus EF divided by KT. Okay, therefore we can write this integral as C electronics is equal to d of EF into KB square T minus EF divided by KT to infinity x square e raised to x divided by e raised to x plus 1 square dx. So I have changed this integral to this. We know that this EF by KT means KTF by KT. So this is of the order of 10 raised to 2. Normally this is 10 raised to 2. Okay. So minus of this thing will become minus 100. You can put this thing as T of EF K square T. This can be written as minus infinity to infinity x square e raised to x dx divided by e raised to x plus 1 the square. Integral minus infinity to infinity x square e raised to x dx divided by e raised to x plus 1 square is, this value is almost, this value converges to pi square by 3. So therefore df is 3 n divided by 2 ef into k square t into pi square by 3. So this will be final expression for electronic contribution of heat capacity to constant volume is pi square by 2 n k square t divided by, this ef can be written as k tf. Okay. So finally pi square by 2 nk t by tf. So this is the expression for the heat capacity. Heat capacity to constant volume due to the electronic contribution. Okay. So anyway, C electronic is proportional to the temperature. Okay. Okay. So this is the electronic contribution. Now the total heat capacity of a solid at low temperature. Low temperature means this temperature is normally very much less than the Fermi temperature and the Debye temperature, theta. You know what is Debye temperature. So if the temperature is very much less than these values, we know that the total heat capacity at constant volume is C electronic plus C lattice. Okay. So C lattice we have already seen. This can be written as C electronic can be written as some gamma into T. Okay. What is gamma? Gamma is pi square by 2 nk by Tf plus A into T cube. You know T cube law of heat capacity at low temperature. So at low temperature, when T is very much less than Tf, the total heat capacity is gamma T plus AT cube. Therefore, now the experimental value of heat capacity can be fitted with this expression. So we can plot the graph of C by T versus T square. So this is C by T is equal to gamma plus A T square. Okay. So we will get a graph of this form. Okay, it's a straight line. So the experimental data points are like this. So if we fit, we'll get a straight line like this. What is the straight line C by T versus T square graph? What is the okay, y-intercept? What is this y-intercept means? This y-intercept means we'll get gamma. This is y-intercept, and this is the slope of this graph. Okay. So this is about heat capacity. So heat capacity of a metal has two contribution. One is electronic contribution, and the other one is lattice contribution, or the contribution due to the phonon. Okay, vibration. So that we have already discussed in the last chapter. So combining these two contribution, the total heat capacity is the at low temperature is gamma T plus ATQ. This is frequently asked in the CSIR as well as the gate questions. So what is the heat capacity? The electronic heat capacity is proportional to T, and the lattice heat capacity is proportional to T cube at low temperature. Okay. At high temperature anyway, this is a constant, which is the 3 Nk. So that is the classical value. The total heat capacity will be 3 Nk. That's all about the heat capacity. Okay. See you.